Right. So first thing is that some potential will be given, right? Some potential energy V as a function of x or U as a function of x will be given. The first thing is to plot the potential, right? The first step is to plot the potential. For example, if you are given the potential is half kx square, we plot this, right? So it's easy to plot this. We know that this is a parabola. If we don't know, there are other steps that we can take to plot this thing. All right, there are other, we'll discuss this in detail. So let's just take this example of u is equal to half k x square. So first step is to plot this potential. Okay, so that is v of x versus x. This is the equilibrium point. Right, we know that this is a parabola. If you don't know what shape the given potential is, then you have to take steps to plot the potential also, right? So let's imagine that we have plotted the potential. Okay, now draw energy lines corresponding to different energies E of the system on the plot for potential. All right, so maybe I can enlarge it a little bit. Okay, so this is how we do it. We first Alright, so I'm sorry. So we need to sketch the potential first. Alright, so first you plot the potential like that. Okay, so here along this axis or along the vertical axis we are plotting V or U, okay, whichever is the case, and then this is the x-axis. All right, so what does this plot tell us? This plot gives us the potential energy at different points. It gives us the potential energy at different points. All right, so now the next point is to draw energy lines corresponding to different energies E of the system on the plot for the potential. All right, you will understand what we mean by this energy line. So suppose these are possible energies. Okay, these lines correspond to different possible energies. Okay, because the height, okay, the height of this, the height from this x-axis has the dimensions of energy because we are plotting potential, right? So this line means it's a line corresponding to constant energy. This is another line corresponding to constant energy, and we can draw any number of lines. Okay, let's call this as E1, E2, E3. So we have plotted potentials and we have drawn lines corresponding to different values of energy. Okay. Now below this, plot the sketch P of x comma E is plus or minus 2m E minus U. We saw this already. Okay. All right. So again, we'll take this, below this, it's easier to plot it like this. We plot x along this line and let's say Px, because we are dealing with one dimensional system. Okay. Just below this, we'll have x and Px, just below this. Okay. Now you see that at points where the energy lines intersect the potential energy curve, right? So at this point, this means that at this particular point, at this particular value of x, E is equal to U. That's what it means. Am I right? At this particular point, E is equal to U because these lines intersect. This is the line, this is a straight line corresponding to definite value of energy. This is the potential energy. So at this point, E is equal to U, right? So at points where the energy lines intersect the potential energy curve, the momentum is 0, right? By this equation, the momentum is 0. If the potential increases in a direction, the momentum decreases in that direction and vice versa, right? So let's just drop these lines here. These are points where the momentum becomes equal to 0. So we need to extend this from 0 to both sides. Okay, this is true here also. Okay, all right. Now we have got to start somewhere. Let's start here, or let's start here, right? At some particular value of we have got to, let's see. Right? Indicate the directions of motion of the representative point by marking tiny arrows on the curves obtained by the previous step. Right? So we have to start somewhere. Let's start at some. We could start anywhere on the phase space. Okay, we could start anywhere at the phase space. Let's start at x equal to 0. This point is x equal to 0 and momentum is equal to some value p1. We start here. What happens as you go towards positive x? All right. So if you go towards positive x, you see that as you move along the x direction, the potential energy is increasing. Okay. As you move along the x axis from 0, the potential energy is increasing. This means that by this equation, the momentum will decrease. So if you start here and go towards the positive x direction, the potential energy, the momentum has to decrease because the potential energy is increasing. Okay, and at the point where E equal to U, that's at the point of intersection, at the point in x where E intersects U, the momentum is 0. All right. Okay. Now what happens? Now you just have to continue. If you go back in this direction, right? If you go back in this direction, you see that if you go from positive x towards 0, you see that the potential energy is decreasing. So the momentum will start increasing in the opposite direction. Okay, and then it will encounter this point where again the potential starts increasing from here, right? Again the potential starts increasing and the momentum starts decreasing, and at this point the momentum becomes 0. All right, then the direction is reversed and again it goes like that. All right, because now the potential is decreasing. When you go from here to here, the potential is decreasing and the momentum increases and it reaches here. Okay, this is supposed to be an ellipse. All right. Now thus, indicate the direction of motion of the representative point by marking tiny arrows. So this is how we drew it. We started from here, so this is the direction, right? So it goes like this. Right? So there's a trick too. There's a rule of thumb to remember the direction of these arrows. We'll discuss this soon. Okay. So this is the phase portrait. No, this is the phase space trajectory corresponding to one particular energy. What if the energy is E2? Okay, this is the phase. Let's say that this is the trajectory. It's the trajectory for energy E1. Okay, what about E2? Okay, if the particle or if the harmonic oscillator has energy E2, then you will get a corresponding curve along this line. Okay, you can actually imagine this thing. You can actually, you can actually imagine this thing. All right. Okay, so you see that harmonic oscillator in the real space, all right, these are not closed curves. In the real space, these are just oscillating, it's not a closed curve, all right, but in the phase space, it's a closed curve. The phase space trajectory is the closed curve, all right, because the system starts at one particular state and then it returns to that state. Okay, it returns to that state. We are assuming that there is no dissipation or there is no loss of energy. Okay, so the system or the representative point must trace paths corresponding to constant energies. All right, and we'll see that paths corresponding to constant energies are actually ellipses for a harmonic oscillator. I hope this is clear. All right, so this is the general idea. We'll continue. Okay, next we said we have to elaborate a little bit about sketching the potential U of x versus x. All right, so we'll have to write down a few steps. So in your examination you will be given a potential curve, potential as a function of x, okay, and you will have to plot it first, okay, just to see the qualitative behavior of it. And then the second thing is to just draw parallel lines, all right, energy lines corresponding to different energies, and then you follow this rule and you get the curves. Okay, so it's an important thing to plot the potential U of x as a function of x. Okay, now I hope so much is clear so far. Let's move on to sketching the potential. Right? Now you can follow this strategy to plot the potential energy. To plot the potential energy versus position curve, we can take the following steps. Okay, first step is to find the points where the potential energy is 0. Find the points where the potential energy is 0. Right? Find the points where the potential energy is 0. Right? So we are actually talking about potential energy. So sometimes I just say potential, but that's not entirely accurate. We have to say potential energy. All right. So I hope you'll correct it in your mind. So find the points where the potential energy is 0. Right. So you take U of x and say that it's 0 and solve this. U of x equal to 0. Which are the points along the line where the potential energy is 0, right? And so you will have this curve, okay, and you will plot the points where the potential energy is actually 0. Okay, you'll plot the points. So you got 3 points now. That's not enough, obviously. Suppose there are 3 zeros or 2 zeros. Let's say there are 3 zeros. We plot all these 3 zeros on the line. We mark all these 3 zeros just qualitatively, okay. Now the next is to find the extremum points for the potential energy curve, right? You need to find the extremum points, okay, the maxima and minima of the potential energy curve. How do you do this? You know how to find the extremum. You just take du by dx equal to 0. Solve this and you will get the points where the potential energy is an extremum. Okay, so for example, let's say that for x equal to a and some value a and x equal to b and x equal to c, I've got an extremum. Alright, so by constructing this equation dou e by dou x equal to 0 and solving it, we'll get a number of points corresponding to the extrema of the potential. Alright, these are points where the potential energy is maximum or minimum. Okay, these are the points where potential energy is maximum or minimum. Alright, we don't know which. I hope this is clear. Alright, so we can just mark those points. For example, let's say okay, let's just leave it at that. Alright, now it's important for us to find whether these points are actually maxima or minima. Alright, whether these points are actually maxima or minima. Alright, so the first step is to find the zeros of the potential energy. The second step is to find the extremum points for the potential energy curve by equating the first derivative to 0. We have got the extremum points. The next step is to find whether these points, okay, these extremum points are whether these are maxima or minima. What do you do for that? Now you find d square u by dx square. Okay, you find the second derivative and put x equal to a. Alright, and if it's positive, then it's a minima. If it's negative, then it's a maximum. Alright, this is the rule. Okay, if the second derivative at a given point, okay, at the point of extremum, we already have these extremum points. Okay, you take each point and find the second derivative at that point. Alright, you find the second derivative and put x equal to a. If it's positive, we know that it's a minimum. If the second derivative is positive at a given point, then it has to be a minimum. Okay, at an extremum point. Alright, if the second derivative is positive at an extremum point, then that extremum is a minimum. Alright, now if the second derivative is negative at an extremum point, then that extremum is a maximum. Alright, now this information will be sufficient usually to plot the potential energy curve, alright, in a qualitative manner. Now, once we get the shape of the potential energy, we draw the energy lines and then we'll draw the phase-space trajectories. Okay, alright. So, find out whether the extremum points obtained in the previous steps by finding second derivative of the potential energy at the extremum. Okay. Find out whether the extremum points are obtained in the previous steps are maxima or minima. Okay, I'll just correct that. Are maxima or minima. We need to find whether this extremum is a maximum or a minimum. Okay, by finding the second derivative of the potential energy at the extrema. So if d square e by dou x square at that point, okay, at these particular points is greater than 0, then the extremum is a minimum, and if it's less than 0, the extremum is a maximum. Okay, I hope this is clear. Okay, we'll look into some examples and you know what I mean by these things. Okay, now there are a few more points that I have collected. These are basically rules of thumbs. Okay, so it's rules of thumb. You can just remember these things and it will help you. If you see a picture, it will help you to do these things. All right. The first thing is that the trajectories of the phase space never intersect for autonomous systems. So for autonomous system means it's not driven from outside or something. The Hamiltonian is the same. All right. You have a Hamiltonian, it's fixed. All right. So provided you don't change the rules in between. Okay, provided you don't change the rules in between, the trajectories in phase space will never intersect. Why is that? Why is that the trajectories can never intersect? Right? We saw that we talked about this conservation of information, right? So for every point in phase space, there has to be exactly one incoming line and exactly one outgoing line. All right. Why is that? Because we know that given the state of the system at any time, this is also known as determinism. All right. The state at any other time is completely determined by the equations of motion. All right. Given the state at any time, this is very important. Okay, this is true generally for all physics. Given the state of the system at any time, the state of the system at a future or the past, the state of the system at any other time is completely determined by the equations of motion. All right. So so the Hamiltonian, generally you have the equations of motion if you have the Hamiltonian. This means that the future of this system or the trajectory or the state of the system doesn't depend on all the history, right? It depends only at the state at a given time. Okay, give me the state of the universe at any time, give me the state of the entire universe at any particular time, the future is completely determined by the equations of motion, all right? Or take the state of the system at any time, state of the physical system at any time, the future is completely determined, which means that once, this is the phase space, all right? Once you pinpoint the point, once you say that this is one possible state of the system, right, then the equations of motion will tell us what's the next possible state, all right, and what's the previous state. Okay, this is completely determined. Am I right? Okay, now imagine two phase space trajectories are actually intersecting like this. Okay, suppose two phase space trajectories are intersecting like this. Now this point is a problematic point, all right, because if the state is given, if the state at this point is given, we don't know what its past is, we don't know what its future is, right? It could be this or it could be this. This means that the evolution in phase space is not unique. If there are intersecting curves, that means that if the phase space trajectories intersect, then that means that there are points in phase space corresponding to which the future of the past are not uniquely determined. If the system is at this point, we don't know whether it will go along this trajectory or this trajectory. Okay, and there cannot be two futures corresponding to a given particular state. Okay, that's not allowed. That's known as conservation of information. That's also known as determinism, etc. This is a very fundamental rule in physics. All right, if you have a state, if the state is given, then its future and past are uniquely determined, all right? These are uniquely determined. There are no two futures, there are no two possible futures, all right? It is uniquely determined by the laws of physics, all right? This is the reason why the trajectories in phase space never intersect, all right? This is only true for autonomous system, because if you change the Hamiltonian in between, all right, then of course the evolution also will change, all right? But that's not the case we are talking about. We are talking only about autonomous systems, means the Hamiltonian is fixed. The functional dependence of the Hamiltonian is fixed, okay? All right. Every point in phase space will have just one incoming arrow and one outgoing arrow, all right? You take a point in phase space, whatever dimensional it is, you take a point in phase space, there will be exactly one incoming line and one outgoing line, okay? Because the laws of motion, it's also known as reversibility, all right? So suppose they intersect, and at this point, right, at this point, we don't know what the past of the system is. It could be this or this, right? Imagining that arrows are like this, right? It could be this or this, but this means that it's not reversible. Okay, so but for physical systems, the equations of motion, the laws of motion are completely reversible. All right. So if you know the state, now you know what the state was in the past. All right, provided you know the conditions and the equations of motion, etc. Right. Now, if at any point the number of incoming arrows exceeds the number of outgoing arrows, then the law is irreversible, and we say that information is not conserved. All right, but information is actually conserved in physics. So we won't have some. So the point here is that the takeaway point here is that the trajectories in phase space never intersect. Okay. Now let's talk about marking arrows. We said that we need to mark arrows on the phase space trajectory. So a rule of thumb is that if the momentum is positive, at a point in the phase curve, then the arrow at that point is towards the increasing x direction, towards the right, right? So if the momentum is negative, then the arrow is towards the negative x direction. How do you see this? So suppose you have got this px thing, all right? In which cases are momentum p positive? All right, p is positive here and p is positive here. P is negative here and p is negative here. So if you have a curve like this, right? If you have a curve like this, you see that the momentum is positive. Okay, in this quadrant, the arrow has to be there towards the positive x direction. All right, also in this quadrant. Right. Similarly, if you have some curve like this here, right? It's in the quadrant where p is negative. This means that the arrow is towards the negative x direction. Okay, that's a simple rule to remember. This is true. Okay? So, for example, once you look at the simple harmonic oscillator, if you look at the simple harmonic oscillator, you see that the momentum is positive here, so the arrow is towards the positive x direction. The momentum is negative here, right? This is the 0 point. Momentum is negative in this quadrant, so it's towards this direction, left. and here again it's negative, so it's towards the negative x direction, like that. Okay, so that's how it is. All right. Okay, the regions where E is less than V. All right, so in the graph you will see that when the potential energy is negative, the energy also, total energy can be negative, but the kinetic energy cannot be negative. All right, so there are regions where E, the total energy, is less than the potential energy. In these regions, these are classically forbidden. All right, because in these regions you will see that the kinetic energy can become negative, which means that the velocity is imaginary, and such a thing does not exist in classical mechanics. Okay, so the region where E is less than V are classically forbidden, and it's very easy to see which are the region where E is less than V. We will see in some of the plots. All right. So the regions where E is less than V are classically forbidden because in these regions momentum becomes imaginary. All right, or velocity becomes imaginary. Now phase curves for periodic motion are simple closed curve because just half mv square. All right, half mv square. Right, if this is negative, that means velocity is imaginary. That's what we mean. Phase curves for periodic motion are simple closed curves. Okay, so periodic motion in real space corresponds to open curves. It's not closed curves, but in phase space, periodic motion corresponds to closed curves. Okay, so periodic motion corresponds to closed curves in phase space. Okay. Now there is a term called separatrix. Separatrices differentiate between different types of trajectories. All right. For example, for the same system, there can be trajectories which are periodic, which are closed, and there can be trajectories which are open, depending on the potential energy at a given point. Okay. So, for example, if you have a curve like this, if you have a potential curve like this, okay, if you have a potential energy curve like this, you will see that this within this region it's closed. All right, it just keeps going like that. Right, but outside this region, you will see that it's free. It is free. The momentum. This is an open curve. It's not what you say periodic motion. Okay, so it will be an open curve. Okay, but in between these two possibilities, for a potential like this, for example, okay, in between these two possibilities, there will be curves which separate between these two possibilities, and these are known as separatrices. Okay, all right. Now, it's also one thing to remember this thing. It's a good thing to remember this thing. Sometimes it will help you to eliminate some of the options. So, if the Hamiltonian does not change under the transformation p going to minus p, okay, suppose the p appears as p square in the Hamiltonian, then even if you put p is equal to minus p, the Hamiltonian does not change. Okay, then the plot will be symmetric about the x-axis because we are talking about px curve. Right? This is where p is positive. This is where p is negative. Alright, so this means that if the Hamiltonian does not change when you go from p to minus p, the shape of the curve will be symmetric. Right? For example, this thing, it's entirely symmetric about this x-axis. It's entirely symmetric about this x-axis. It's also the same for x. If the Hamiltonian is invariant under the transformation minus x going to minus x, this means that this is x, this is positive x, and this is minus x. The curve will have exactly the same shape about the p-axis. It will have the same shape about the p-axis, or rather it will be symmetric about the p-axis. Alright. Now let's look at a general example. Right. Some of the points are illustrated here. Okay. So this is the potential energy curve. This is the potential energy curve that we have. These are the energy lines E1, E2, E3, etc. Alright. So this is x, u versus x, and this is v versus s. It also could be p versus x. Okay, it doesn't matter. You see that this is E1, E2, E3. Now, you look at this E1 line. All right, you continue this E1 line. You see that here, this height is the energy. All right, this height is the energy. This height is less than this height. All right. So, in this region, the potential energy is less than. The total energy is less than the potential energy. Okay, it's clear that if you extend this line for E1, right, if a particle is with energy E1, then this region is forbidden. This region, okay, this region along the x-axis is completely forbidden because inside this E is less than V. All right, so this region is forbidden. This is a forbidden region. Okay, that's one point. All right, this corresponds to this line corresponds to E2, some other energy E2, and you see that at one point E2 is equal to U, right? At some point E2 is equal to U, right? So that will correspond to separatrix, because this is for E3, you see that it's completely unbound, right? It's completely unbound. It can go anywhere except beyond this point. It cannot go beyond this point. Alright. Now suppose a particle is with energy E1. Right? Suppose a particle is with energy E1. Suppose it's coming from infinity. Right? When it comes from infinity, it sees an increasing potential energy. Right? We said that P is equal to square root of plus or minus square root of 2m E minus U. Right? This is just to get the qualitative behavior. When U increases, P decreases. So suppose a particle is coming from plus infinity with energy E1. Right, with energy E1, it will come here, it sees more and more of the potential energy, because the potential energy is increasing when you come from the positive, let's say plus infinity. The particle is coming from plus infinity with energy E1. Okay, so it sees an increasing potential energy, correspondingly the momentum decreases, and at this point the momentum becomes 0. At this point the momentum becomes 0. Right? It cannot cross this point. Because this region is classically forbidden. So for a particle for energy E1, right, the left side of this part is completely forbidden. It cannot enter this part. Okay, so it sees this potential, it comes to a rest and then turns back and goes back to infinity. Alright. Now suppose for particle E2, particle of energy E2, it will come here. Alright, it will approach this point like this. Alright, it will approach this point, and depending, alright, so it will just approach this point, alright, this is coming from plus infinity. Alright, so a particle with starting with a positive momentum, alright, it will go along this line. Alright, so this is an example for a separatrix. Okay, for this point. Right? If it's more than this, you see that the particle coming from plus infinity will come here, its momentum will slow down, its momentum will decrease up to this point, right? Its momentum will actually decrease, but it never comes to 0, right? It decreases and then again increases, like that it goes. Right? Similarly, let's look at some other region. Right? This is a general curve, right? Just to illustrate the idea. Now let's look at this part. Let's look at this part, right? This part. So this corresponds to some other energy E2, and it's already within this region, all right? It's already between, let's say, this x1 and x2. Okay, so what happens corresponding to that? You see that you have a closed curve, all right? Because you could start the particle with any momentum, but as it goes towards the plus x direction, the momentum will decrease. It will come to a halt at this point. Right, because at this point E is equal to U, right? It will come to a rest, so momentum goes to 0, and then it's this thing, all right? So momentum will go to 0 and it then just goes like that. But now corresponding to this line, you see that we have got a different kind of curve. That's known as a separatrix. Right? We have got a separatrix. Okay. Now if it's like this, if the energy is like this, then the particle is confined between, let's say, this x1 and this x2, and we have some sort of a periodic motion, because at this point the momentum is 0. These are turning points, all right? These are turning points. Okay, so you can look at the qualitative behavior like this, right? So if given a potential, if we have a potential energy curve, we can simply, just by looking at it, we can draw the phase space diagram. Okay, all right. So for higher energies, you see that for higher energy, a particle coming from plus infinity, yes, its momentum will decrease, but it never goes to 0. It just keeps increasing and decreasing, and at this point it comes to rest. The momentum becomes 0 at this point. All right, because at this point E is equal to U or P equal to 0, and then momentum increases in the opposite direction, and then it goes back to infinity. All right, this is the general description of it. Let's do just one example before winding up this session, and we'll do more problems in the next class, okay, in the next session. We'll just do the phase portrait for a simple harmonic motion. We already discussed this, but we'll go through it in some more detail. The phase space portrait for a simple harmonic potential V of x equal to half kx square is equal to half omega square x square is sketched. All right, how do we sketch? So it's easy to see that this is an ellipse. All right, because what's the conservation of energy condition? We say that half. We can say that p square by 2m plus this is the kinetic energy. What's the potential energy? It's let's write it as half k x square is equal to some energy E. Okay, this means that p square divided by 2me plus half k x square is equal to 1. We just divide throughout by E. Okay, now we can write this as p square divided by 2me plus x square divided by 2e by k is equal to 1. Right? What is this equation? This is of the form x square by a square plus y square by b square is equal to 1, and this has to be an ellipse. This is an ellipse. Okay, so we immediately see that these are ellipses. Right? Depending on the energy, these are ellipses with different what is the major and minor axis. Right? The energy determines the major and minor axis. All right. So it's clear that this is an ellipse. Okay. And there is an interesting point called the equilibrium point. All right. At x equal to 0, there is a point at x equal to 0. The one trajectory I missed out earlier. Okay. This is the potential energy, and we draw the curves like this. We said that if the momentum starts at some positive value, it just makes a closed curve like so, right? What if the momentum starts at 0? What if p is equal to 0? Okay, then it will remain at x equal to 0, and this point is in itself a trajectory. Okay, this point is in itself is a trajectory. Okay, because if p equal to 0 initially, x is equal to 0, and it will remain there all the time. All right, it will remain there all the time. P equal to 0 and x equal to 0. I'm sorry, p equal to 0 and x equal to 0. That corresponds to a particular energy, and it will remain there forever. That's the possible trajectory of the system. Okay. All right. That's what the system at x equal to 0, v equal to 0, or p equal to 0 remains at the same point forever. The trajectories are ellipses. All right. I've plotted it here. So the first thing is that this plot is the plot of the potential energy curve. This is the plot for the potential energy curve, and we see that this is corresponding to different energies. We have got ellipses. Just as I said, when E at the points where E intersects the potential energy curve, the momentum becomes 0. Right? So these are what do you say, ellipses corresponding to turning points. Right? The energy determines the turning points. So right, these are ellipses with turning points. Let's say x1 and x2 and x3, x1, x2, x3, x4, etc. And we have got ellipses here. Right? So this is not very difficult. And other regions are classically forbidden. Other regions are classically forbidden. All right? For example, if you just extend this energy line here, okay, at this point we see that this height is the energy. All right, but the height of the potential energy is this. Right? So we see that this is a region where V is greater than E, or E is less than V, and it is a classically forbidden region. Right? Likewise outside here. Right? So the system cannot access the entire x-axis from -infinity to infinity, because there are regions which are classically forbidden. Okay. All right.